Hello. So today I want to give the solution to problem 8 on the sample midterm 2. So these all involve linear, homogeneous ODEs with constant coefficients. We have some of order 2 and some of order 3. I've highlighted the two that you're most likely to see in applications in physics and engineering. All right, so let's just head into it. One more little thing about the overall form, right? We're going to find the characteristic equation, and I'm going to use R as a variable. The scan solutions use K. I did that in a previous semester. So we're going to write down the characteristic equation, find the roots, and then we got to know how the roots correspond to functions. And I need two different linearly independent functions here. I'll have a C1 and C2, and these guys will all have a C1, C2, C3. All right, so let's head into it. This first guy here, the characteristic equation is R squared plus 16 is 0. So the roots are R is plus or minus 4i. All right. So that means that the solution is y is c1 cos 4t plus c2 sine of 4t. Okay. Now what about this one? We have r squared minus 16 is 0. So the roots are r is plus or minus 4. Okay. So here you get y is c1 e to the 4t plus c2 e to the minus 4t. But you notice that that's not on your list of possible solutions. And as we've talked about before, the sum of these two divided by 2 is cosh of 4t, and the difference is sig of cosh t. So another way of writing it is y is c1 cosh hyperbolic cosine of 4t plus c2 sinh of 4t. And that's the one that's on the multiple choice list. And this is a really nice form if you can solve an initial value problem. Y of 0 is c1. Y prime of 0 is 4 c2. Okay? All right, let's think about this one here. We have r minus 3 squared is 0. So the roots are 3 and 3. That's with that squared factor. That's what we mean by having a root of multiplicity 2. And so the solution here is y is c1 e to the 3t. That's 1. That comes from the root of 3. But I can't write plus c2 e to the 3t, right? That wouldn't be, that couldn't be a general solution because for these two functions are linearly dependent, or another way of saying it is, there's really only one constant, c1 plus c2. So the rule is I put in a factor of t. Okay, that's what the multiplicity 2 does. That multiplicity 7, I get 7 functions. The original e to the r, e to the rt, t to the rt, up to t to the 6 e to the rt for multiplicity 7. All right, we'll get to one later like that, I think. All right, what do we got here? So that can also be written as e to the 3t times c1 plus c2t. And that's the form that's in the multiple choice options. All right. What's the next one here? This is r squared is 0, so r is 0, comma 0. And this has a general solution, y is c1 plus c2t. Now, before I go on to these third order, let me say a little bit about these two. Right? This is what you get from a mass on a spring. Right? And the solutions are simple harmonic motion. This, from Newton's law, says the acceleration of some particle is 0. F equals ma. A is 0, no force. And if the acceleration of the particle is 0, the particle moves with a constant velocity. Any initial position is possible, any velocity is possible, but it just has to be constant. All right, so now let's go on to these third order guys. Here we've got r cubed plus 4 equals 0. And frankly, I have no idea what the roots are. There's 3 of them, counting multiplicity. That's one thing I know, because it's a degree 3 polynomial equation. So hopefully that's hopefully the solution to this differential equation isn't one of those you can choose from. All right, what about this one? Here we get r cubed minus 8 is 0. So I want a cube root of 8. Actually, I do know one of them. 2, if I plug in 2 here, 2 cubed minus 8 is 8 minus 8, which is 0. But the other 2 I don't know. If you know a little bit about complex numbers, you could probably figure them out, but we don't, just let's hope we don't have to deal with these guys. So what about this one? R minus 2 cubed equals 0 is the characteristic equation. So the roots are r is 2, 2, 2. All right. So just kind of like what I talked about before, let's get straight to this. The general solution is y is e to the 2t, and I'd have c1. That's what I'd get with just one root, a constant times e to the 2t. But I have 2 roots of 2. I need to put t times c2. Okay. And then another root, I have t squared times t2 times c3. Okay. All right. So I always have 3 arbitrary constants for an order 3 differential equation. All right. And here we get r cubed is 0. So the roots are 0, 0, 0. And this one is y is c1, because e to the 0t is 1. So I don't have to leave that. I don't have to write that. c1 plus c2t. When do I stop? Well, I stop and I get 3 constants because it's order 3 ODE. Now, mathematically, this also kind of makes sense. A little bit like that, but that's more physics, 0 acceleration. Here we're saying, give me the most general function whose third derivative is 0. And the most general function whose third derivative is 0 is just a quadratic function. In fact, it could be linear too. We wouldn't call this a quadratic function if c3 were 0, but it's still a solution to that differential equation that c3 is 0, right? Okay, so hopefully you're pretty good at going back and forth between the equation, the roots, and the functions. All right. And then, as we mentioned before, sometimes we have to think about, like with the annihilators, sometimes we give you a function and say, what's the differential equation for which that is a solution? In other words, what operator will annihilate the function? For instance, what operator annihilates t e to the 3t? That operator does, d minus 3 squared. When that hits t e to the plus 3t, I get 0, because that solution, t e to the 3t, is a solution of that differential equation, so that is the annihilator. All right, bye.